On to this third one. An object travels along a straight line path, so its position is given by a function of time by the graph shown. What's the magnitude of the object's constant acceleration during the interval of time shown in the graph? So, first things first, when we're looking at a position versus time graph, the first thing we do is, when we're looking at any graph, first thing we do is look at the axes to determine what they are and make sure we know what the units are. There's nothing weird going on here. Okay, so what is the magnitude of the objects during the interval of time shown on the graph? Well, the points where we're accelerating pretty much seem to be from this point right here to this point right here, right? So this is our initial position, and this is our final position. So let's guess this thing and see what we've got. We know the initial position is going to be 10 meters. The final position is going to be 20 meters. The time in between those two is going to be 1 second. And I think that's it. Right, because it's kind of curving here, it's curving here. So we're going to be looking at this right here where we have constant acceleration happening. How do I know it's constant acceleration? This velocity right here seems to sharply change towards the end, whereas this is a more gradual. So I'm thinking that's what it is. The unknown is we're looking for acceleration. Now notice that this thing says specifically constant acceleration. That is a huge hint, an enormous hint, that using one of our constant acceleration equations is appropriate. Okay? And these equations only work if our acceleration is constant. If it's not constant, then we're going to have to look at something else. So what equation can we use? We have x naught xf. That's pretty obvious. We're going to use that displacement equation, which is the xf equals x naught plus v naught times t plus 1/2 at squared. Uh-oh, there's something in there that we don't know. Do we have to do more work? Let's see. The initial velocity. Well, that's going to be at the starting spot. And what is the velocity at that starting spot? That's right. It is 0 because the tangent line here is exactly flat. So that means all of this will just go to 0. So we're good. Next, in our substitute, let's see, we have xf 20, x naught 10 plus half of a times t squared. Well, we know t squared is going to be 1 squared, right? And we know half of 1 is 0.5. Okay, so we'll do some mental math here. We're going to move that 10 to this side, so we get 10 equals 0.5a. Dividing each side, we get our answer. Our acceleration, our constant acceleration is 20 meters per second squared. That's it. Not too bad. Next up, we have engineers working on a vehicle stopping ability. On each trial, the vehicle is given a different initial speed. When the brakes are applied, the distances that that the car travels before it comes to a rest is also measured. Data shown on the graph. What is the best estimate of the magnitude of the vehicle's stopping acceleration? Alright, so first thing, we have different initial speeds. Looking at our graph, because we're presented with a graph, and the first thing we're going to do is look at the axes and the units. Stopping distance, meters, initial speed, meters per second. Kind of a weird graph to see, right? We don't see that normally, but this is a very common graph when you're looking at vehicle data. When the brakes are applied, the distance that the vehicle travels before it comes to a rest are also measured. Alright, so comes to a rest. So what does that mean? That means our final velocity is going to be 0 because we're going to come to a stop. So then, how about from this graph, what can we pull? We can take an initial velocity. Any one should work. I'm going to use 20 because it's a round number, and I want to. You can use 10, whatever. Anything should work. What else? We're not given any time. At 20, our stopping distance is 20. So xf equals 20. Believe me, that says 20, even though you can't see it. Unknown, we're looking for the acceleration. Which equation are we going to use? We have initial velocities, x, a. We have no time, so we'll use the no time equation. Vf squared equals v naught squared plus 2a delta x, where our initial position is 0, so the final minus the initial is just going to give 0. So not to 0, but you know, the x naught is going to be 0. Final velocity squared, so we have 0 squared. Don't forget the squared. You're going to forget the squared. 20 squared plus 2 times a times 20. I'm going to go down one more line here just to do all this. 400 plus 40a equals 0 squared, I think is 0, but I don't have my calculator, so I'm just going to go with it. And I'm going to get 400 on one side, 40 on the other side. Are you still watching this? Divide by 40. Oh no! Negative 400, because we're subtracting 400 from each side. Divided by 40, and that's going to give us our acceleration of negative 10. Yep, that's perfect. Circling of the answer. Deal with it.